In this video, I'm gonna go over some problems that you should know for your Chemistry 2 final exam. So I'm gonna start with this one. What is the equilibrium constant for the equation below? And we've got the equation. So, and then we've got 4 choices. So a couple of things that we should know for this problem. So one is the definition of the equilibrium constant. So basically, if you have a stoichiometric equation that kind of looks like this, the equilibrium constant for this equation will be the concentrations of products multiplied together and to the power of their coefficients, the respective coefficients, divided by the concentration of the reactants to the power of their multiplied together to the power of their respective coefficients, like that. And part 2 that you need to know is all of the ingredients, all of the reactants and products that actually participate in the equation, equilibrium constant equations, have to be liquids in the liquid form or ionic form. So they have to be diluted in water in order to participate as part of the equilibrium constant equation. Okay, so if you have a solid that's entering the equation or leaving the equation, solids are excluded from the equilibrium constant formula. Solids, they are excluded. So based on these 2 knowledge points, we can go ahead and solve this question. First, let's take a look at the actual equation. So we have first reactant in its aqueous form. Second reactant is also in the aqueous form. The product, if you notice, one of them is solid, which is the lead iodide is solid. So it should not be participating in the equilibrium constant equation. And then the second product is sodium nitrate, which is also aqueous, or in its ionic form. So now it's going to be very easy for us to see which one would be the correct answer here. So it looks like for part A, we obviously do have sodium iodide, I'm sorry, not sodium iodide, lead iodide included, so that would not be correct. For part B, we do have one of the products listed on top and to the power of its own coefficient, so this part is correct. The lead iodide is omitted, which is correct, and then also it's divided by the concentrations of the reactants, which is correct. So this could be potentially a correct answer. So let's go through the rest. So it looks like here it is including the lead iodide as a solid, but excluding the sodium nitrate as in ionic form. So this is obviously incorrect. And then in part D, it looks like they are reversing the reactants and products. So the reactants are actually listed up on top and the products are listed at the bottom. So that's obviously incorrect. So it looks like the only correct choice that we've got here is option B. So next question. What element is being oxidized in the following redox reaction? So we have a redox reaction here. And then we need to know what element is being oxidized or what element is losing electrons. So the word, so oxidized in this case means an element is losing an electron in the reaction process, or electrons, so it could be losing one or more electrons. So in this case here, we need to find answer or an element that would do that, right? So now as a rule, kind of like as a general rule, neither oxygen or hydrogen gain or lose electrons. They kind of just keep their own charges. So in this case, then we can get rid of option B and option D right away. So now we have option A and C to work with. So we need to figure out which element, either manganese or carbon, is the one who would be losing electrons when it's moving from reactant to the product phase. So let's just check it out. Let's go with manganese first. Well, in order to do that, we need to actually figure out what charge manganese has over here. Like in the product phase, manganese obviously has +2 charge, but here in the reactant phase, we actually don't know what charge manganese has. So how would we do that? Well, we know that oxygen always has a -2 charge. So oxygen always has a -2 charge, but we have 4 oxygens. So if we have 4 oxygens, it's actually going to be -2 times 4, which gives us -8. So the charge of the O4 here is -8 charge. Okay, so now the charge of the whole ion for manganese oxide is -1. So we need to take that into consideration. So if we have -8 minus -1, we get -7. So if we took into consideration the charge on the oxygen and the charge on the ion itself, in order to counterbalance, we get the -7. So in order to counterbalance this charge, we have to assign the +7 charge on the manganese. Because if we have -8 on the oxygen plus 7, we have -1. And -1 again is the charge of the whole ion. So that's why +7 is the charge on manganese. Okay, so now if we go over to the other side for manganese, it actually +2. So it looks like manganese is not losing electrons. If it was losing electrons, it would have a higher positive charge than 7. But it actually has lower positive charge than 7. So therefore it actually gained 5 electrons. It gained 5 electrons here. So therefore it's not being oxidized. So manganese we can remove. So now the only option we have is the option A, but let's just double check and we'll do our balance on carbon just to make sure that it actually is being oxidized. Okay. So we start with the hydrogen. So hydrogen always has the +1 charge, but 2 hydrogens would make it +2 charge, right? So that means that the whole C2O4 part would be -2, okay? So, and we know that oxygen is always -2, but if the 4 oxygens would make it -8. And in order to keep the -2 for the whole C2O4 part, we're going to have to assign the C2 part +6. Because if we have 6, +6, minus 8, we got -2, which is the total charge for the C2O4 part. So obviously +6 is assigned for the total 2 carbons. So in order to make the carbon single, we gotta divide the 6 by 2. So the charge on the single carbon here, is +3. Okay. So now let's just see what the charge of carbon here on CO2 is. Now it's a neutral molecule. And we know that oxygen charge is -2, but 2 oxygens give us -4 charge. And since it's a neutral molecule, to balance it out, we give the charge of +4 to carbon. So looks like in this case, carbon did get more positive. It went from +3 charge to +4 charge. So it actually it actually lost one electron. One electron it lost. So therefore, it is carbon. Carbon is the one that is being oxidized, or choice A. Okay, so in this question, which has got the same exact equation, but the question is different. What element is being an oxidizing agent in the following redox reaction? So in the previous question, it was asking what was being oxidized. And in this case, they're asking what is an oxidizing agent. Okay, what element is being an oxidizing agent? So it's very easy to make a mistake and assume that it's the same exact thing. So if element that's oxidized and then oxidizing agent, so even though they sound very similar, they're not the same. So element that's being oxidized is the one that is losing one or more electrons and gains a more positive charge. Now the oxidizing agent is an element that kind of makes it happen. So it's going to be completely opposite of that. So if an element, if an element is being oxidized, it's gaining electron, then the oxidizing agent is the one that actually would be losing an electron. So if we have, it would be this case. It would be the opposite case. We know that element that lost the electron is the carbon, right? So carbon actually lost one electron. But the element that gained electron is the manganese, because manganese went from +7 to +2 here. So manganese is the one that actually gained like 5 electrons. And that's the one that made for carbon to lose the electron. So this way the answer is C, manganese. So next question. What is always true for the equivalence point of a titration? And we have 4 different options. So just to remind you what a titration is, basically if you have unknown concentration of acid, say acid, and you're trying to figure out what the concentration of this acid is, you can add to it the base of the known concentration. And when you see a drastic change in pH, that's when you know that the equivalence point has been reached, and then you can actually calculate the concentration of the acid. Okay, so that's pretty much what the titration is. And I just mentioned the word equivalence point. So equivalence point, so something is equivalent, right? Equivalence point. What is it that's equivalent? Well, basically it's when the acid and base quantities are equal, in a mixture, or when mixed together in a mixture, and the quantities are based on stoichiometry. So they're based on stoichiometry. So what's that mean? So stoichiometry is basically balancing a chemical equation, right? So it's balancing a chemical equation. So you have HA plus BOH. So if you have acid and you're adding some sort of base to it, you get the salt, which is BA plus H2O. So this is based on the stoichiometry. So in the stoichiometry means that it's based on the amount of moles. It's based on the amount of moles. Molar concentrations. Based on that, we can pick our answers. So answer A is moles of base equal to moles of acid. Mass concentration of base equals mass concentration of acid. Volumetric concentration of base equals volumetric concentration of acid. Or D, when pH shift from acidic to basic. Now we know that A would be correct answer. B and C are definitely incorrect. Definitely incorrect. Now D could be an option, but you have to be careful with D, right? Because the way the concentration curve goes, the way the titration curve goes, I guess, it goes, so if this is pH, this is amount added, so amount of, in this case, so we say base added. The concentration will go like this, then there's be sharp rise up, and then it will level out again. So the equivalence point is somewhere over here. Now this is good for strong acids and bases, but if you have weak acids and bases, then the equivalence point might look something like this. It will not be as sharply defined. It will kind of be like this, and the equivalence point might be not at 7.0, but maybe somewhere over here. So that's why it's not quite right when you say from acidic to basic. So now for strong acids and bases, the pH where it switches might be 7, but for weak acids and bases it might be 8 or 9. So technically 8 is a basic pH, but it's just but the weak acid or weak base are just achieving their equivalent point. That's why point D, option D, is incorrect. So the only correct option here is option A. Alright, next question. Why does the plot show vertical jumps at the melting and boiling points? Check all that apply. Now here, please pay attention to the words check all that apply. This means that not just one option is available, but maybe 2 or 3, or maybe all 4. So you just got to be kind of careful and select properly. So we're given the chart, the graph of entropy versus the temperature. Right, so and we have 4 different options. Option A is the enthalpy doesn't affect the entropy. So let's review what the entropy is. So the entropy is the amount of randomity. So entropy is the same as randomity. So the more randomity is in the system, the more entropy, the higher the number of entropy, or the higher the entropy is, right? So the enthalpy is the amount of heat, total heat that's in the system. So the amount of total heat in the system. Okay. So if it says here, the enthalpy doesn't affect the entropy, this would be incorrect, because in order to increase the entropy, in order to increase the randomity, you have to increase the enthalpy. For example, if you go from solid, like ice, to liquid, the system has to have more heat in order to do that. So therefore, you have to increase the enthalpy in order to increase the entropy. And then obviously, as it goes to gas, again, you need to increase the enthalpy in order to increase the entropy. So enthalpy and entropy kind of go together. So A is incorrect. Option B, the entropy increases when the state changes due to higher randomity. So let's look at this. So it looks like it hit a state change at this border over here, and then it's the entropy just jumps. It jumps up without changing the temperature. to the next level. So it goes from lower point, which is here, to higher point, which is there, even though the temperature is staying the same. So option B in this case is correct. The entropy increases, so we see that the entropy increases when the state changes, and the state changes, this is the state change line, due to higher randomity. So as if you think about it, if you have a solid, the crystals are kind of stuck together. Crystals are stuck together in a solid, right? They're not moving. Now in liquid, all of a sudden, as it goes to liquid, the crystals break apart. The crystals break apart, and then you have particles that are starting to move around. So the entropy increases. So the entropy increases because it goes from solid to liquid. The state changes. You see the state of change due to higher randomity. Yes, the randomity increases because here the particles are sitting still in the solid. They're not moving. But as they go to liquid, they start to move around more. So this answer is correct. Now let's continue because we see it says check all answers that apply, right? So we're going to continue and look. Option C. The temperature does not affect the entropy when changing the phase. So what it's saying is that the temperature is not changing, but the entropy can change. So this is correct. So the temperature, so once it hit that critical point of phase change, the temperature can stay the same, but randomity still goes up. So the temperature doesn't have to increase as long as there is phase change happening, as long as there is enough temperature or enough enthalpy to make the change happen, the phase change happen, the randomity will keep increasing. So this option would be correct. The temperature does not affect the entropy when changing the phase. If it was affecting the entropy, we would see that there would not be this fast jump without changing the temperature. Now let's look at option D. The entropy decreases when the state changes due to higher randomity. So it says the entropy decreases, so the entropy actually going down when the state changes due to higher randomity. Well, this is obviously incorrect. So the entropy goes up and randomity goes up because the state changes. That's what happens, not the opposite. So this D part is incorrect. So the correct answers here are B and C. All right, following question. If the spontaneous reaction is carried out at a constant temperature and pressure, the equilibrium state occurs at fill in the blank. So we're given this chart, and then we have 4 choices. So what does this chart tell us? So we got free energy on the y-axis, and then we've got the extent of the reaction or the equilibrium constant for this reaction on the x-axis. And then it kind of shows us where the equilibrium occurs. So the equilibrium here occurs right at this point. So that's where the reaction starts to, the concentration of the products and reactants kind of equates. So they stay the same at the equilibrium point. They're no longer changing with time. That's pretty much what that says. And it's basically saying that in order to get to that point, the processes have to be spontaneous. You cannot push them. You cannot increase volume or temperature, etc. artificially. If you just mix the ingredients together and you just let them be on their own, they come to the equilibrium point by themselves or spontaneously, and that would be the equilibrium point. But it's showing where the free energy would be in order to do that. So free energy is basically the amount of energy that system has that it doesn't need. It just sits there freely. Just think about the potential energy. So if you have, say, like a mountain with a dip like that, and you have a ball that's sitting on top of the mountain. Well, this ball actually has the potential energy to go down. The ball has the potential energy to go down. So this is the potential energy of the ball. So this is potential energy of the ball. Well, it's very similar to the free energy in chemistry. So the reactants will keep on reacting and changing the concentration until it hits that dip, until the potential energy or the free energy. So if you keep going down, 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 the ball will end up right here. And basically your potential energy here is 0. And the same thing with the free energy. So the free energy, also it's called the Gibbs free energy. So the G will be 0 at this point. Okay, so now that we know this, let's check out our answers here. The highest point, so if the spontaneous reaction is carried out at a constant temperature and pressure, the equilibrium state occurs at the highest point of free energy. Well, this is very obviously incorrect. So the highest point of free energy would be somewhere over here, like that, but it's obviously not. So A is definitely not correct. Now B, the lowest point of free energy. So this actually might be correct. So this is potentially our correct answer, because it is, as you can see, the lowest point of, so the free energy here can be here, can be here, but if it still has free energy, it's just gonna keep on going. And same thing with the products. They might go up here, but then eventually they will level back down until the free energy is used up. Now, next thing is when Q is more than K. So K is the equilibrium constant, is where the reaction balances out, right here. And then Q is at any point of the reaction. So you can calculate the Q, or just, it's kind of like a Q is the extent of the reaction, where the reaction is. Like, so the reaction can be right here with the reactants just starting to react. The reaction could be over here. So this all would be Q, 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 Q. This is K, this is the equilibrium. And again, this is all Q. So this is the extent of the reaction, but not the equilibrium, not the constant. It's not going to balance out over here. It's going to balance out at the equilibrium constant, but not at the Q. But say for, say, the first 2 seconds, it might be over here. So this would be Q. For the next 2 seconds, it might be over here. So this would be next Q. For the next 5 seconds, it might be up here, it could be next to you, and then maybe in 10 seconds and eventually balance out and will not change the concentration. Well, that will be your K equilibrium. So if you think about that, this says when Q is more than K. Well, Q is more than K, let's see, let me change this, is right over here. This point here between there and there is Q is more than K. Actually, at this point is Q equals K, because the extent of the reaction is equals to the equilibrium constant. So this is incorrect. Now, when delta G, or free energy, is less than 0, well, so D would be incorrect. So the only correct answer here is option B, which is the lowest point of the free energy. All right, so one more question. So consider the reaction. We got zinc in solid form is mixed with copper in liquid form. And then the product is zinc in ionic form or liquid form plus copper in a solid form. So the question is, why does the intensity of the blue color lessen? And then we have 4 options. So what do we have here? What does this picture actually tell us? Let's look at that. So the blue color here is the copper, because copper is in the ionic form. So first it says aqueous here, and then if you see, it has +2 charge, which means it's an ion. It's the ion. It's an ion. So this is copper 2+, the liquid. Now zinc is in solid form, so, and look at this, this is a piece of metal, this is a piece of metal, so this is zinc with the charge of 0, and it's solid. So as they sit here like that, what is happening is part of the zinc, part of this metal is going into liquid. So part of the zinc, so zinc is going into liquid. So now if this is 0, this is zinc, 2 plus. And then part of the copper, so part of the copper that is liquid is going into solid. So this liquid copper is going into solid, and it becomes copper with 0 charge. So this is what's happening. Now let's look at the question. So why does the intensity of the blue color lessen? So based on this equation, it looks like copper is what's giving this blue color to the liquid. So, and if you look on this one, the blue color kind of goes away, but then we see the black or really dark metal starts to settle on a strip, which is basically tells us that this copper from blue color, from blue liquid, goes and settles on this zinc strip, and therefore the liquid part is less bright, less blue, because it's losing that copper hue. So let's look at the answers that we've got. Copper ions settle on the strip and oxidize. So copper ions, so we have copper ions in the liquid, they settle on the strip and they oxidize. So let's see if they actually oxidize or not. So we have copper 2 plus, and it's going to copper 0. So it's actually gaining some electrons. It's gaining some electrons. So it actually gained electrons. So when it gains electrons, it actually reduces. So it doesn't oxidize, it reduces. So this part A is incorrect. Now let's look at part B. Copper ions settle on the strip. Yes, they do. They do settle on the strip and reduce. So again, we just figured out here, because copper is gaining electrons, it reduces. So this part B is correct. But let's go through the rest of them and to make sure that we are definitely correct. So copper ions separate from the strip and oxidize. Well, this is incorrect because copper ions were not on the strip to begin with. This is solid zinc. So this is definitely incorrect. And then D, copper ions separate, actually spade means separate from the strip and reduce. And again, they don't separate from the strip. They were there to begin with in liquid, and then they settled on the strip. So this is wrong. So the only option that's correct is the option B. Copper ions settle on the strip and reduce. If you found this video helpful, please subscribe to my channel or come to my unlimited chemistry study room, where I can give you one-on-one unlimited help with any questions you may have as you prepare for your exam.